So my name's Brooke. I'm going to be giving a talk on Witchcraft library, and just going to do a really informal poll off the top. Who here has used Elixir before? Awesome. How many people use it in your day job? One person. Awesome. Okay, cool. All right, we'll get started. Also, if there seems to be some problems with the lapel mic, so if nobody can hear me, someone in the back, just wave and I'll speak louder. So. Yeah. All right, so Elixir. So when I was taking a look at Elixir a few years ago, and then the end of last year again, kind of confused by why doesn't it have all the stuff that I'm used to from all the other functional programming languages that that I've come to know and love, right? So flip, ID, const, fix, currying, all of these niceties. Where have they gone? And then I realized that this was really me just asking, how can I make this more like Haskell? Which is a variation on the bulb paradox, which really just says any language that you're used to writing in, if it's missing some, when you compare it to another language, if you're missing any features, you don't understand how somebody could live without them. And any language that has features that your favorite language doesn't have, you don't understand why somebody would want that. So I started with, how can I make this more like Haskell? Witchcraft seemed like a good name for this because a lot of people approach these types of abstractions as being esoteric secret knowledge. Hopefully, these libraries mitigate that. And yeah, a lot of people I've spoken to, over the years have talked about these mathy abstractions as if they were just absolute dark magic. They don't understand what's going on. It's scary new stuff. It doesn't have to be the case. This quote seems to be floating around a lot during this conference, but it's one of my absolute favorites. So the purpose of abstraction is not to be vague, but to create a new semantic level which one can be absolutely precise. So precision gives us a lot of nice things. We can leverage the last 60 plus years of research, port features from other languages, get nice patterns. We can think of these as functional design patterns, and it also lets us be free of edge cases for any of the properties that we've guaranteed. So I wrote 3 libraries over the holiday break at the end of last year, bored. So they together sort of form like a Elixir Z, or Elixir's. Quark gives you a lot of the common combinators and currying. The currying in particular is both, there's a runtime version, just a function, and a macro at compile time. Algae for data types and algebraic data types. So you get your maybe, either, tree, free, and on and on and on. And Witchcraft, which gives you some of the more common algebras and category theory type constructs, functors, applicatives, monads. In the roadmap, we have arrows and category and bifunctor and all the good stuff. And values for all 3 of them, as one sort of meta project, are to lower the barrier of entry for these kinds of abstractions for people. Be consistent with the Elixir language itself as much as possible. Be pragmatic so that if something is just, we're used to seeing it one way in math and a different way in Elixir, do it the Elixir way. Keep the barrier of entry down, make it idiomatic, and have a strong emphasis on teaching. So providing a lot of documentation, examples, doc tests, so people can see how these things can be used in an actual setting. So what does this get us at a high level? We can start thinking about things on a strategic level instead of implementing things just always right down, in the nitty-gritty detail. Generalization gives us very reusable code, right? And makes it very semantic as well, which is nice. We like to be able to, as functional programmers especially, we like to be able to look at our code and say, this is what it means to the computer, as opposed to, this is, just instruction, 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 instruction. And because we're abstracting out common patterns, it needs, that part of the pattern at least just needs to be tested once. It works, great, and then you can apply it to many different situations. And then fun. It's fun to port stuff, right? So here's an example of fixed point combinator, right? So factorial function, the standard way with manual recursion passing the explicit state through. We have to have the extra parameter and then thread it all the way. With fix, we can write just the guts of the calculation just once for a single pass, as opposed to having to deal with the entire recursion, and then pass it to fix, and we get the same end result. We get a factorial function. It also makes it really nice to test because now we don't have to test the entire recursion. We can test just that one chunk of code for a single pass. And then, of course, you probably still want to have a feature test that ensures that, yes, your inputs and outputs are correct. It does the right thing, but you don't have to worry about how it's doing the recursion. Another example, using applicatives. So this is going to work on any data type that applicative is defined for, which is just done with the protocol. You'll see the definition of it later. In the example, there's just 3 helper functions. Those aren't actually part of the applicative itself. That's what we're going to be applying to. And we're going to be we just pipe a list through 2 functions in a list, and we get back the result of each of those on each function concatenated together. The one thing that you'll notice if you're coming from a language like Haskell, or if you've used applicatives before, is that the notation's backwards from what you'd normally expect, right? We have a list going into functions, not functions getting mapped over a list. And this is largely because in Elixir we're used to thinking about piping, right? And so your data is what's flowing through a program, as opposed to running a function over top of data. If you really like to think about running things over top, there's a reverse operator on all of these functions that lets you do it the Haskell way. Because things associate one way, in some cases you will need to use brackets, but not always. And it also, because we have now an abstraction, this doesn't work just for lists, this works for any data type that's an applicative. And so we can think of it as being a little bit more semantic. So lists are often used to represent non-determinism or returning multiple results from a computation. Maybe, on the other hand, can represent emptiness or nothingness in computation. And so the same function can operate in both of these contexts. And we can leverage properties too. So whenever we have these algebraic properties, for example, a monoid is something that has an identity element and a way of combining 2 things to return something of the same kind of thing. So integers under addition for a monoid, right? 0 plus anything is whatever that thing is. So 0 plus 10 is still 10. And whatever you add together, you're still getting back an integer, right? And so we can start thinking structurally about a lot of our problems. We can break up a problem in a monoid so that, sorry, I should actually back up. The other thing that it gives you is associativity, so that you don't have to worry about your brackets, right? So as long as things are happening in the same order, it doesn't matter which operations happen in what order. Right? As long as the end result happens, A, B, C, D. So you could break up expensive computation, send them out to a bunch of different nodes, and they don't have to be equally weighted. You could give half of this computation to one node and then, little chunks to everyone else, have the large node compute, half of it, and as long as they all come back in the same order, everything works out just fine. And then hypothetically, because this is going to hypothetically, right, you could then use this abstraction to do it not just over, say, integers. It can also work on any monoid, so lists or integers under different kinds of different kinds of operations, on multiplication instead of just sums, right? And then release it as a library instead of just a single application, and then people don't have to keep rewriting the splitting code and the reassembling code. They can just define a monoid, and boom, it works immediately. For the downsides, there is a higher barrier of entry when you're using abstractions. A lot of them can be pretty mind-bending at first. And it puts the burden on the programmer up front to have to learn these things. I would argue that the same goes for any technique, right? Anybody coming from an object-oriented background has had to learn some gang of 4 patterns. We all know what a factory is, right? We are trying to mitigate this as much as possible in these libraries with explanatory docs, examples, keeping them relatively extensive. Different ways of thinking are compatible. So this does require breaking the Elixir model a little bit, as I alluded to before. We need a lot of partial application to get generality. So just because we have a function that takes 3 arguments, we need to be able to apply a single argument at a time, and we don't know ahead of time, because we're writing very abstract code, how many arguments higher order function is going to be taking. So everything gets auto-curried immediately. So all your functions take 1 argument at a time up to the number of arguments that they actually take. Elixir is an arity-based language, right? So foo with 2 arguments is a different function than foo with 3 arguments. It still maintains the correct arity inside of the wrapping, but it is wrapped up. Bootstrapping these tools into Elixir requires additional tools that aren't baked right into the language. Right? We need dialyzer and quick check in particular. Dialyzer to give us types, quick check to let us test properties, and we'll be looking at that really briefly a little bit later. And then directionality. So in Elixir, we really, as I mentioned before, really like to think left to right, data flowing through functions. It's very sort of horizontal in nature. In math, Lisps, MLs, we often think in terms of properties and structurally, geometrically about problems. Things don't necessarily reduce out in a nice direct pipeline flow. So how do we unify these? Well, you can think of them as being 2 separate dimensions. So data flow is obviously a horizontal dimension. That's really easy to think about. It flows with time. Abstract functions are also often composable. And your abstraction can be thought of as a vertical dimension. This also, another way of thinking about this is strategy versus tactics, right? So tactics is the nitty-gritty implementation, on the ground, looking at exactly what's happening. Whereas your strategy is thinking, from a much higher, your 30,000-foot view. I'm going to do this general thing, then this general thing, then this general thing. It also lets you decouple your thinking from the specifics, and so then you can go in and define all the properties that you want on a data type, and then once you have that defined, you can go and look at the strategy that you're going to approach the problem with. So this is kind of a very loose visualization. This bottom blue line is typical piping function. Pipes can contract horizontally. So Phoenix, for example, at the very top level is 3 functions piped together. But that's a very zoomed out view, right? If you dig deeper into each of those functions, they are themselves pipelined functions. Abstractions themselves also compose, right? You can compose together functors, and you can compose together modic binds and arrows and all of that stuff. And you can think of something changing its level of abstraction over time, right? So as you apply arguments to a function, it becomes less abstract, right? It's more specific. Here's another example of that. So map can be represented in terms of a fold, right? So the enum map, which comes with Elixir, could be defined as a right fold or a right reduce in the parlance, with a couple of its arguments fixed, right? So there's the Elixir and the Haskell version there, or using an applicative and applicative functor and regular functor example, we can fix the structure of a computation and have that become less abstract as well, right? So it's no longer just an applicative apply. This is now has an addition and an F map and an apply in sequence. So let's talk about types. Maybe there we go. There they are. So we can port in algebraic data types, more or less. A lot of people have been trying to do this. When I was looking to do this, I did a bit of research and I saw a lot of stuff that looked like this, which is actually super idiomatic in Elixir. We often reply with an OK, for example. And then a lot of these as well. So having a struct to represent the state of, in this case, a maybe, which could represent either a value or nothing. The problem that I find with this bottom case is that you can have something and have it also say that it's nothing at the same time, right? Just some value and nothing true, which seems like a contradiction, right? In the common or the more idiomatic Elixir version, the problem here is that nothing doesn't necessarily mean an error. Nothing might be a valid part of your computation, right? You might say, look for a file. The file's not there. That might not be an error. That might be an expected possibility, right? So sure, Elixir doesn't have ADTs, but we can fake it with structs. So in this case, we have maybe, which then has submodules nothing and just, which each define structs. Nothing is the interesting one here. It's a struct that has no fields, right? You can't add a field to this at all. It exists purely to have the type. You can still pattern match on this in a function, right? It'll just be, percent nothing, squiggly braces. And then we can define the type union on the third line there as saying the type of maybe is just or nothing, right? We can't enforce properties in Elixir, but because we have protocols, we can fake it, right? So this is the applicative protocol, for which we have to just define wrap and sequence with the correct type specs on them. For our data type, we really just have to define those two, and we get out of it several functions and a bunch of properties immediately. So very low level of effort required. You get all of these properties immediately for free. Right? It uses all of the functions that fall out of, and operators that fall out of having those just two functions defined. And we get our class hierarchy. So every applicative functor is also a regular functor. And we can run all of the functor code, all the functor properties immediately within the applicative scope. The other thing that this gives us too is, because we have all of these properties, we can optimize our code, unfortunately by hand. The compiler isn't aware of these things. If I can find a way to do it, I will. But for example, the homomorphism property, on the left-hand side, you see it's wrapped value applied into another wrapped value is equivalent to just wrapping a value, right? If you find those in your code, you can go through and change them to the simpler version, and everything is exactly the same, except it runs a little bit faster, which is great. So, in summary, Abstractions is a handy tool. Pipes are compatible with other abstractions. You can think two-dimensionally, think with properties as well, and though we do have to break the arity model, we can use that to fake a lot of functionality that we have in other languages. So that's the end of my talk. Please feel free to contribute open issues on the GitHub tracker, or get in touch if you have ideas, thoughts, concerns, feelings, etc. That's how to get hold of me. Thank you. It sounds like I actually have a couple minutes. Does anybody have questions? Yeah.
So if I were to learn Elixir and start a clean slate project and buy into all of this kit,
Yeah.
Is there anything left that would not be able to be checked at compile or test time with like a Haskell or Scala type system?
Yeah. So I haven't gotten super deep into Dialyzer, but it's a different kind of type checking. So not everything in the system has to be type checked. In Haskell and Scala, you have type inference, right? So as much as things are typed, you'll get all of those guarantees. Something that came up in a previous talk earlier today is to check those properties when they're defined at compile time, so that you don't have to run them separately. And I was like, oh, I guess I could probably do that in my library too. So that's something that's going to be coming eventually, if I can swing it, that you would also get in some of these other languages. Less so in those two, more in a language like Idris would have that, right? So, yeah. Awesome. Okay. Thank you.